So welcome. This is the usual announcement. I just want to say I sent you an email yesterday. If you have responded to that email, that would be good. If you haven't, please read and then give me a response. Okay. And if you know some friends who are not usually here, but you know the friend is taking my course, please help me by spreading the news. Just tell your friend to read the email and respond to me. It's very simple email and it takes a bit of time for you, but then hopefully we can avoid some trouble if we face trouble. Okay, if we face some difficulties, some last minute difficulties, at least I have a chance to respond to that. And your data will be maintained by me, and this will be deleted after the end of the course. Okay, so maybe 1 week or 2 weeks after the final exam, I will delete everything, all the emails and all the data you sent me. Okay. Do you have any question about the arrangement of the midterm? No? Okay, so let's begin. Let's begin our lecture today. Okay, so what did we cover last time? Last time I overran a little bit, but we completed this story. So I would like to start from that. This is from last time. We spent time to develop the thermodynamics for a magnet. And in the end, I applied what we developed to show you we can do cooling. Okay, so this is one of the key figures that you should recognize. Last time we developed a few partial derivatives, and I told you the meaning of those. If you want to achieve cooling, this is something you want to have. So these two partial derivatives are the key ones that you should understand. And this is a more realistic picture showing the entropy as a function of temperature. And from here, we know how to achieve cooling. You can start from some field, zero field, and then you do this isothermal magnetization, and then you do the adiabatic demagnetization. Okay, and this is the way for you to reach low temperatures. It's actually a very realistic case. Now, I put this 4.2 as the starting temperature. For example, if you are able to reach a temperature like this, then you can imagine how powerful this is, right? Actually, liquid helium is not very easy to transport. Now, suppose you want to do some very low temperature physics, not on the Earth, but in space. How do you transport this liquid helium over there? It's not easy to do the experiment. So one thing you can do is to do this kind of magnetic cooling, because once you are out there, your ambient temperature is already quite low. And if you want to cool down your detector, for example, to reduce the noise level, you can take advantage of the ambient temperature, which is a very huge reservoir for you. And that will guarantee you a very nice starting low temperature. And you can play this trick and go down to lower and lower temperature. Okay, another thing I should say is you can also imagine doing this at different stages. So for example, you don't reach all the way to here, you reach somewhere here, and then you cool down. And then you do it again in steps, and that will allow you to go to lower and lower temperatures as well. Okay, I want to start from here because here there's a very important observation that we should make. That is, this graph doesn't label 0. But if you think a little bit deeper, if you, for all these different curves, you must have all the curves to meet at zero entropy when you reach T equals 0. That is to say, you should reach zero entropy at the zero temperature limit. Otherwise, you will have some very funny result coming out. Okay, so this is the motivation of the third law. Okay, so put it another way, if you have the third law of the thermodynamics, it guarantees you that all these curves must meet at the origin. Okay, 0, 0. So it's 0, 0 on the ST plane. Otherwise, you face some very strange results. Okay, so just very briefly, third law. Now, I redrawn this in a more schematic way for me to develop my argument. So third law is again based on empirical observation. So you see the, so this is based on empirical observation. So based on, and that's why up to this point you shouldn't be surprised to see all these statements. Okay, so if you read my notes, I give you all the different form of third law. So for example, you have Nernst statement, you have Planck statement, you have Simon statements. So all these are developed based on different kind of experiment. For example, experiment in chemistry lab, you have a different statement. But if you want to summarize all of them in a simple word, basically this is what I say. So third law tells you the entropy goes to 0 as you cool down to 0 temperature limit. Okay, now this is nice for us because we have been talking about entropy change since the beginning. This might give you some impression that we only care about the entropy change, but not the absolute value of the entropy. This is not the case because once we know how to define the absolute entropy, we can, for example, if you look at Gibbs function, if you look at the differential form, you see there's this term here. All right, so here, if you look at this S, this entropy, this is some partial derivative of Gibbs with respect to T. So if we know the absolute value, this is not written in the change, this is written in the quantity itself. And therefore, it's actually meaningful to have some scale given for this entropy. And we don't want to just know the change, we want to also know the absolute value. And that's why this gives you a nice set point that you can compare with. So how do you evaluate the entropy change? You try to compare with the 0 temperature value, which must goes to 0. And when very soon, in 20 minutes, you will start to do statistical mechanics. Another place to remind you is in statistical mechanics, we define the entropy. This is a statistical entropy. Okay, we define it this way. That is to say, we must be able to attach an absolute value to this entropy, not just the change of entropy. Okay, this is not written as delta, this is written as S. Another thing, maybe a preview, is the following. If you learned statistical mechanics first, then come back to look at thermodynamics, this is probably not too difficult for you to accept. Here is, sorry, you are right, you are right. So G is a TP. So this, I will change. Yes, you are right. Actually, I get two message is about this. Okay, so G is a function of T and P. Okay, So the note also is also wrong. Okay, so I will correct that. Thank you. Okay, what did I talk about before we? Okay, so statistically, you have this statistical entropy. And how do you get zero? So here you don't have much freedom to get zero. The only way you can get zero is when you have omega equals 1. Okay, so that is to say, you are in a very well-defined ground state, and therefore this omega, this tells you how many different ways to give you this outcome. The only way to give you this outcome is when everything is at a well-defined ground state, and this is something you achieve at the base temperature, the zero temperature limit. Okay, so in this case, this statistical entropy will be 0 if omega is 1. Okay, so for a very big chunk of the course, we are going to learn how to deal with this omega. Okay, so looking at these two diagrams here, this is something you should relate to the adiabatic demagnetization I mentioned earlier. So I told you, you must have this situation. This is a good situation. And this situation will give you some trouble. Why? Now, imagine this X to be magnetic field. This is what we did when we talk about magnetic field. Okay, I'm going to flip to that slide to show you. And this is schematic. This is more realistic, but look at this. This is this curve is taken at b equals 0. So these are the same magnetic field, constant magnetic field data. Okay, suppose you have a process at x1 that takes you along this curve. Suppose you are able to travel along this curve, then you have something very powerful. You will be able to do cooling like this, like what we mentioned before. You do the isothermal process from x1 to x2, then you go back to x1 by adiabatic process. And you keep repeating this, and very soon you realize you'll be able to reach absolute 0 and below. Okay, so in order not to be able to have this situation, or you can put it this way, based on a lot of experimental data, we know we cannot reach absolute 0. And for this to be consistent with thermodynamics, we must demand the entropy to reach 0 at the 0 temperature limit. So you close this curve. Okay, so third law tells you entropy goes to 0 at 0 temperature. And the equivalent way to say that is the following. You can also say that third law tells you you are unable to reach absolute 0. So this is the usually written like this. This is written as absolute 0 temperature is unattainable. So unattainability of absolute 0. Okay, so that's it. Basically, this is a very quick summary of the third law. Okay, now this is not the only thing which is happening when you have this third law. You have quite a few consequences. So I'm going to use the lecture note and show you some of them. Okay, so first you will have So first, what is the consequences of the third law? Okay, first, what you have is all the heat capacity mass goes to 0 at 0 temperature limit. Okay, why? Because you write the heat capacity like this. Okay, whatever the x, let me write one more step. So you have this, let me put this T inside. Whatever the x, which means whatever the process, at zero temperature limit, this cannot change. Entropy cannot change. So at zero temperature limit, whether you are traveling along the x1 or x2, it doesn't matter. You have no change in the entropy at the zero temperature limit. And your log T at the zero temperature limit will goes to infinity. And the entropy change will be zero. And therefore this C sub X must go to zero. It doesn't matter what is the constraint you put. Okay, so just remember, it doesn't matter what is this constraint. So for the usual PV system, it doesn't matter whether we are talking about CP or CV. Okay, this should spell some trouble for you right now. And this trouble is actually something important. This trouble is what gives you the hint that ideal gas model must fail at zero temperature limit. Okay, and we will see that soon. And actually, let's talk about that. Why do we not expect the ideal gas model to work there? You can give several reasons. One reason is you can suppose you know more about the microscopic details. You can work on the assumption of the ideal gas model. You look at this assumption and figure out what's wrong with the assumption or with those assumptions. So you know, when we talk about ideal gas, we treat all these gas particles as independent particles. Okay, suppose you are lucky enough to go to very low temperature and these gases do not condense. It's still fair to ask yourself, is it reasonable to assume you can ignore the interaction when you are at low temperatures? Okay, so when you bring this distance closer and closer, you expect the interaction to become important. And in that case, it's not too surprising that the ideal gas law would fail at low temperature limit. Another thing is, if you can also look at thermodynamics. So when you calculate the difference between the heat capacities, for ideal gas, you must have this relationship. Okay, but when you are at the zero temperature limit, all the heat capacities goes to zero. All heat capacities go to zero. It doesn't matter whether what kind of constraint you apply. And therefore, you can never satisfy this relationship. Okay, so there's the saying, ideal gases are no longer ideal there. We are going to meet we are going to reach this conclusion again, but from different approach, from a different direction when we do statistical mechanics. Okay, and this is kind of thermal expansion has to stop. Okay, this one is not very difficult. There is, but one thing you can appreciate probably is you learn how to use Maxwell relation again. Okay, thermal expansion is written like this. It's not that obvious that thermal expansion has to stop. That's to say this beta must go to zero at zero temperature limit. To do that, you need to convert these partial derivatives into the form that you can apply the third law. So you convert like this. This is one of the 4 Maxwell relations developed for PV system. And you will see the entropy is coming here. Okay, so when you are approaching zero temperature limit, this cannot take any finite value. Okay, so beta has to be 0. Okay, next is about Curie's law. And here is again the same thing. This is something we wrote down 2 days ago. We already have the entropy we want here, so that is no problem. And then the other thing, relating this entropy, related to the entropy is the temperature derivative of chi. Okay, here, remember we say this chi, partial derivative of chi with respect to temperature has to be negative. But here, no, negative, but this, you should read it like this, has to be finite and negative. But if you apply Maxwell relation again for the magnet system, you reach a conclusion which is very similar to the PV system. That is to say, this quantity has to approach zero. Okay. Now, again, this is can be understood by looking at the assumption why we had this Curie law to begin with. Why did we have the ideal gas law to begin with? We ignore the important and the difficult details. That is the interaction between the particles. And here, what are the interactions? The interactions are the interaction between the magnetic moment. We assume a magnetic moment doesn't care about other magnetic moments. That is to say, we assume them to be independent, non-interacting. And this is the kind of assumption that will break down when your thermal energy becomes very small. So at that kind of energy scale, your magnetic energy scale will become dominant. So your moment, any given moment can feel the presence of the other moments. Okay, so this is again, not too surprising. Okay, finally, this is something fun. This is something I can draw for you. The slope of the phase boundary has to be horizontal when you plot it on the PT diagram. So this is pressure versus temperature diagram, just like what you learned before when we talk about the phase diagram of H2O. Okay, and there you probably already seen something like this. When you reach zero temperature limit, this slope has to be zero. So this curve has to be horizontal. Why? This is actually quite simple. This is coming from Clausius-Clapeyron equation. If you write dp dt, this is precisely the equation. And from that equation, this gives you the slope, and the slope has to be zero because S1 and S2, any process that happens at zero temperature has to give you the same entropy. So if you cross from here to here, from phase 1 to phase 2 at zero temperature limit, this has to be the same. Okay, and the volume jump is still there. So if you go from a superfluid phase to solid phase, you still have a volume jump because this is a first order transition. So this is finite, this is zero, then the slope must be zero. Okay, and tomorrow's exercise class, TA will talk about helium again. So we will see something like this again. Okay, so this is, I don't know what else can we say, maybe something for you, some take-home message for you is this is helium-4, and this is a pressure scale. So if you want to reach the liquid helium state, your boiling point of liquid helium is 4.2 at 1 atmospheric pressure, so it's somewhere here. Okay, and then you cannot solidify helium unless you apply pressure. So maybe this is some take-home message for you. At least this is those common knowledge a physics student can appreciate. Okay, so if you're at 1 bar, 1 atmospheric pressure, you can liquefy helium. You can have the gas and you can liquefy. And this phase transition is very important in the history of physics, because of this property, we could do low temperature physics. We can have access to a property of material below this temperature. But in fact, if you cool down further, liquid helium undergoes another phase transition into the superfluid phase. That's to say, the liquid will flow without viscosity. It's a bit like the liquid equivalent of superconductivity. So there, what you're talking about is the electrons will move without resistance. Here, your fluid will flow without is a non-viscous flow. And if you want to stabilize a solid, you need to apply pressure. So you have to go to this phase. Okay. All right. So that is everything about thermodynamics. But don't assume that you can just forget everything about thermodynamics, because the design of this course is to try to explain some of the stuff we developed earlier, but using statistical mechanics. Okay, any question? What is the range of high temperature? This depends on the interaction scale. So basically you are comparing, so you have to compare a few energy scales. So one is the magnetic field. Okay, so what is high? What do you mean by high? High, usually for this kind of question, it's not easy to understand how high is high. Okay, so actually we are going to do this Curie law. We are going to derive Curie law, but I give you a preview. So you will have, if we talk about simple, S equals 1/2 moment. And there we are going to analyze the situation using the partition function. And you have two relevant energy scale, mu BB, and the energy scale due to temperature, and that is the KBT. Okay, so we are going to analyze the case of the situation of the limiting cases. And that is to say, when we talk about high temperature, we are going to assume KBT to be much, much larger than mu BB. Okay, now what gives you this, and why do we have this relevance of that? Because this, you should not just imagine this to be the field energy. This is also how we draw the energy level for this system. So we are going to draw the two-level system. And this separation between the two levels is proportional to mu BB, with a G factor in front. Okay, so that then depends on the separation of the energy level. And somewhere, so in the limiting case, KBT much larger than mu BB, this is what we call the high temperature. And the opposite limit is what we call the low temperature. Okay, as usual, the intermediate case is always a bit more tricky to handle, and you need to be more careful with the assumption. So for the purpose of deriving the Curie's law, we are going to see this behavior. Okay, that is to say, I want my thermal energies to be so large that I do not care the detail of the separation. So basically, if I draw this pictorially for you, that's to say, I want to have enough sufficient energy for my system to hop between the two, such that I do not even need to care about the separation between the two levels anymore. So that is the high temperature limit. Okay, S equals 0 for all processes. So this ds is the difference between the entropy when you reach the same point with different processes. Let's say you have a process like this at 0 temperature, you move vertically. Of course, we cannot really reach precisely T equals 0, but you can see the limiting cases from the figure earlier. Let's say we get very close to T equals 0, and we move from here to here. Okay, so what we are saying is the change of the entropy will be the difference between the entropy associated with the solid phase and minus the entropy associated with the superfluid phase, and this difference has to be not significant at T equals 0 limit. Okay, another way to look at this is you need to define what is ds. So I will look at it as the difference. So here, I will say the difference between the entropy here will be noticeable, right? So we pick a a temperature to discuss. So I should cut this vertically. So if I cut it here, the difference between the entropy at x1 and x2 will be significant. And when I cut to this vertical cut at lower and lower temperature, I will approach zero difference. Okay. All right. So let's move to the. Actually, this is a good time for a break. It's a bit earlier, but if you don't mind, let's do a quick break now. And I would like to finish everything about statistical mechanics I plan to present. Wait a minute. Okay, I take it back. Let me start first, and then I will see where's a good place for a break later. Okay, so statistical mechanics. This is very fun. In the past, students reported that they're enjoying all this counting. So I hope this group will also enjoy this this physics here. So we have about 10 lectures left, right? So from today until the end of the course is about 10 lectures. So in these 10 lectures, we need to cover all this material. But don't worry too much. If I cannot finish, I will make up. In this kind of setting, it's easy to do makeup. I can even just stay home and then give you a video later. Okay, we don't need to worry about rooms and we don't need to worry about your time slot. Okay, so first I would say I will try to make the note self-contained, which means in principle for this part you do not need a textbook. The reason is the following: there are so many textbooks out there, and Blundell is quite good, but it's not quite suitable for this level. So there, the book is using a lot of ensemble theory, which is something we don't want to do. Okay, so I recommend a few textbooks there, which you can read. They are available in the library, but not as electronic copies. But as I say, the notes should be, I will make my best attempt to make it self-contained for you. Okay, what is the M we are going to head to? Okay, so we already talked about equilibrium. Equilibrium and macroscopic physics. Okay, so this is what we call the thermodynamic. And this is the thermodynamic description. Okay, so this is first part of the course. And I'm sure a lot of you are taking Professor Hui's quantum mechanics. But even if you don't, you should appreciate that in when we go to very small scale, the language we use is to use quantum theory to describe our microscopic world. So macroscopic world, we have thermodynamics. We talk about something very big, relatively big, something like a container with fluid, and that we can do experiment using piston, and this piston is something you can see. And on the other extreme, you have something you can, most people can hardly see unless you are really working in this field. Okay, but you develop a lot of intuition because of those courses. Okay, so this is the QM description. Okay, so I would say we would use statistical mechanics to bridge these two extremes. Okay, so what I'm saying is I'm not going to repeat quantum mechanics. I'm going to do a little bit. My main interest is not to talk about the property of Schrodinger equation. I'm not gonna talk about all this operator theory and how to get all this, how to solve the Schrodinger equation based on different potentials. So this is not my aim. So my aim is very simple. I assume you know how to solve the problem. I'm going to just go and pick these energy levels and use them. Okay, so what we have is here you have all these discrete energy level, which you already solved. And you solve it for me. I don't care how you solve it, but you already solved them. And I'm going to, based on this, I'm going to do my statistics to get the distribution. Okay, and my aim is to see whether I can gain some predictive power to describe my thermodynamic system, which I care about the volume, the energy for a given number of particles in this collection. Okay, so this is an example of this would be like your exam score. So your exam score, the thermodynamic description will tell me what is the average of the exam score. Let's say we have a class of n students and the average is 67%, and this is my thermodynamic result. And the quantum description will be listing all the scores, like student A will get 40%, student B 70%, and so on. Okay, and somewhere in between is the distribution, those histograms that also allow me to gain some insight about the learning outcome, the teaching effectiveness of the class. Okay, so another thing to emphasize, which I already say, is we are not going to worry about interacting case. So not focusing. This is 1S or 2S. I can never remember. Not focusing on interacting case. So if you pick a book, that's why there are many books out there. There will be books that start from this level, non-interacting case, and that is something we want. Because when we write the energy of the internal energy of our system, non-interacting case will appear very different from the interacting case. So non-interacting case, we don't need to care about the interaction energy. I can have a very quick way to just do some accounting. I do some survey. I go around and see all the energy levels. And then I count how many particles are occupying that levels. And I can do a simple multiplication to work out the total internal energy. Okay, that is why we are only going to focus on non-interacting case. And we are not going to discussing different ensemble. Okay. Now, strictly speaking, I want to warn you here, is a very minor detail, but important. This interaction, what I mean non-interacting really is let's say is very weakly interacting, because I want to talk about thermodynamics. I want to be able to talk about thermal equilibrium. Okay, so the interaction is there just to make sure I can reach thermal equilibrium. That's the only purpose. So the interaction energy will still be ignored. Okay, we are not discussing ensemble theory, but it doesn't mean those who know ensemble theory or those who will learn ensemble theory next year will not appreciate what we develop here. So what we develop here is called the micro canonical ensemble. So by the time you realize, you learn ensemble theory, hopefully you recognize that what we have developed so far is called the micro canonical ensemble. Now, what is this? This is actually the equivalence in the thermodynamic sense is actually written here. That is to say, we want to keep the number of particles, we want to keep the total internal energy of the system and the total volume constant. Okay, this has an advantage too, because if you keep the volume constant, you do not need to worry about this discrete energy level changing. Okay, so when you solve particle in the well, after you solve this problem, you can write the energy eigenstates as a function of the principal quantum number n. So most people stop here and say, oh, all the energy levels are given by n. Once I change my n, I get different energy level. But if you look very closely, the size of the well actually enters there in the formula of the energy. So if you want this same set of n's to give you the same discrete energy level, you better make sure the size of the well does not change. Okay, that is to say, if we generalize it to a 3D well, we do not want to get into the complication of having different volume. Okay, and if you want this kind of complication, there are tricks to do this. There are other ways to do that, and that will be covered in the next course. Okay, so maybe the single most important example to kick off is look at the problem of flipping coins. So I'm going to flip some coins. Okay, so this is an example which we should study very well. So I'm going to take 4 coins. What is the next page? Sorry. So I'm going to take 4 coins. And we are going to flip them one by one. And then look at the outcome. Okay, so 4 identical coins that we can really distinguish. 4 coins, 4 distinguishable. 4 distinguishable coins. For example, we put them, we align them along the table. We know this is the first, second, third, and fourth. Or equivalently, we flip the same coin, flip 1 coin 4 times. Okay, so this is a toy model, but a very important one. This is the toy model. This is the toy model for distinguishable particle. Now you can appreciate this a bit more. Now coins, you only have 2 outcomes. If your coins are the same as mine, you only have head and tail. So what I'm going to do is to give you the way to do statistic on this. And you can also appreciate that if I talk about spin 1/2, I will have to actually just the coin problem, because I can only have spin up or spin down. Okay, so if I have a huge number of them, then I can distinguish. And how do I make sure I can distinguish them? That is not that difficult. I take a lattice, and then on each lattice side, I put my spin. That is to say, I know the address of this spin, and the problem is actually identical to the coin problem here. Okay, so this is why this example might look very simple and innocent, but it's actually quite far-reaching. Okay, what are the possible outcomes? So the possible outcomes, for example, I'm going to have I'm going to flip one coin 4 times. The first time I maybe get a head. Second time I get head. Third time, fourth time. So this is one possible outcome. Or I can first time I get the head. Now these coins are even, so I can also get the tail. I can get another tail. I can get another tail. So this is another possible outcome. Okay, and this is called the microstate for this problem. Okay, and the list, of course, is long. Yeah. And now, very quick, how many microstates can we have for this system? And this one you can, you must be able to do. Total number of microstates. Now, when I flip it the first time, I can have either head or tail. And likewise, it's an independent event. So the second time, I will have 2 different outcomes. So in total, I will have 2 to the 4, which is 16. So this is the total number of microstates. If I have time, I can list all of them. And this is what you can do in principle when you try to do statistical mechanics. You take your system, analyze it, and list all possibilities. Okay. All right. So I'm going to analyze this more after the break. Now, this is a good time to take a break. And yes, after the break, I will continue this, and then we will very quickly list to 2 postulates of statistical mechanics. Okay, so you can let's come back at 1:30, shall we? Now it's 1:22, so come back at 1:30. Okay, so welcome back. So before the break, we talked about this situation of 4 coins. Okay, so according to according to your experience, you know the total number of microstates will be 16 anyway. You can list this out. You probably have done this before in the past. Okay, so I think these will be the total number of microstates. The important point is, if I should maybe give you another microstate, which is tail first, then I have head, tail, tail. Okay, obviously at this point, you should appreciate that these 2 are not the same microstates. Okay, so this is, although they all have 3 tails, but that is not the same microstates. Okay, but you can also ask yourself this question. If your aim is to get an overall of 3 tails and 1 head, then this is a different scenario. This is a different story. Because in that case, both of these actually qualify to serve the same purpose, to give you the same outcome. Okay, so let me say this again. Although these 2, these are different microstates. So these are different microstates. But I can ask myself, I can define a scenario that I want. I can say I only care about if my aim is only want to have 3 tail and 1 head and 1 head. Then both these and these can help me to achieve the goal. Contribute to this goal. Okay, and what do we say? And here we say, so we say, in this case, this HTTT and THTT belong to the same macro state. So this is an A here. Okay, so from this simple scenario, you can begin to see the picture emerging. This is what you observe. Let's say you do thermodynamics, you observe something. And why do you really see this? The reason must be related to the occurrence, the frequency of the microstates that contribute to the same macro state. Okay, so I will show you this table here. This is something you can find the node. You can draw this yourself systematically. So this is the number of ways to flip the coin 4 times to get all head. So you get only 1 scenario, and likewise for 4 tails you get 1. And according to your experience, if you have a lot of coins, or you flip the same coin many times, if the coin is even, most likely scenario will be you will have half of the occurrence to be head, the other half to be tail. Another way to say that is you take 100 coins, for example, same coins, you put in a box and you shake it. Okay, and then you carefully open that and then count how many tails you have and how many heads you have. You find that the situation is most likely half and half, or not too far away from that. Okay, and here, this is the reason why you get that is simply because that particular observation, that particular macro state you find has a lot of supporting, contributing microstates. Okay, so this is the important message I want to deliver. And this number here is called a frequency. Another term is thermodynamic probability. So this is not the normalized probability because they don't sum to 1, but still it tells you the relative chance to have a particular macro state. So this is the macro state corresponding to 2 head and 2 tails. Okay. All right. So here, using this coin problem, we can write down 2 postulates. One, for a system in equilibrium, all microstates, are equally probable. Okay, so all these, if the coins are in indistinguishable, we have other factors to count. Okay, here we have to be able to tell which coin we are doing. So so this transition will happen when we talk about gas later. So we are going to first talk about distinguishable particles. Then we will talk about indistinguishable case. So don't worry. Okay, so it's when you do the counting, you have to multiply by some factors. So here, Poon, at this moment, you ask this question. It's a very good question, and you should also keep in mind that we are talking about distinguishable case first. So just make sure this stick to your mind, because you ask this question, it's most likely this will be the case. And we will have a way to treat the indistinguishable case, which is harder. Okay, but not too much harder. But so basically, this is something you need to worry about when you do the partition function. Okay, so right now when I say this, it's not too meaningful, but it will become clear later. Okay, postulate 2, the observed macrostate is the one with the most microstate. Okay, so these are the two very important postulates that we need to use. So for the coin problem, you will have 6 microstates here, corresponding to the macrostate of 2 head and 2 tail. So that is the language we want. Okay, so you have 6 microstates corresponding to 2 head and 2 tails, and this is 1 macrostate. Now here you might complain that these numbers are very close, 6 and 4. It's not very. There's not much insurance policy available for you to guarantee that you will have this macrostate. If you have this complaint, congratulations. This is completely valid complaint, and you should really appreciate this complaint. The reason is this distribution will sharpen up very quickly when you have larger number of flips. You only flip 4 times and you hope to build a distribution, and this distribution is bound to be very broad. So this is a broad distribution, which means the peak is not very sharp. And that is the key of doing statistical mechanics. When we do statistical mechanics, our interest is to ultimately analyze a problem with tons of particles, a huge number of particles. And you will see this, this postulate really work very well over there. After all, if you only have 4 such a small system, you can actually write everything down. You don't need to do much statistics. You just write it out and then analyze the problem. But the power here is to go to a very large N. Okay? But still, coming back to the coin problem, let me show you what I meant. So if you only have a small system size, which means small n, this n is the system size, the total number of particles. You see, you have a very broad distribution like this. This is not even, I don't know what's the number here. But the point here is this sharpening will happen when you increase the number of particles. Okay, if all microstates are equally probable, why we will have some states with the higher probability? Okay, this is a very good question. Anyone wants to answer this? The answer is given actually. I will show this table. Okay. Now look at this question, everyone. If all microstates are equally probable, why we will have some states with higher probability? So please, there's a very quick way to fix this statement, then you will be perfect. Huh? Rephrase it, please. No. Okay. Okay. Nearly done. Okay. Poon has the answer. These particular macrostate has higher probability because it has 6 associated microstates, and each of them, and all these can happen with the equal probability. Okay. So you have equal probability of having you have equal probability of having HHTT and HTHT somewhere. Okay, but both of them correspond to the same macrostate. So that is why if you only look at the macrostates, the frequency is higher because it's 6. You have 6 associate states. Okay, so if you look at Poon's statement, if you change that typo, microstate to macrostates, then you will have the answer. Okay? Maybe a bit confusing. Sorry, I try to do it as careful as I can. Is it okay? Okay, so coming back to this coin, what we want to say is this. When you have the large number of coins, if you construct that table, you will have something like this, very, very sharp peak. Okay, right now you have, what do you have? You have 1, let me draw 1, 1, 4, 6, right? You have 1, 4, 6, 4, 1, so 1, 2, 3, 4, 1, 4, 5, 6, 6. So this is n. This is occurrence. This is a number of microstates. Sorry, this is the number of. If I draw this same vertical axis, and then I have another one is 6 and 1. Okay, so this is a very broad distribution, and this corresponds to tau, and this will be H. And this 6, you know, is listed on the table. You have TH, you have HT, and so on. Okay, but this number of heads is half of the number of flips. So this is a key result that we want to deliver. Okay, and this is called the most probable. This is called the most probable macrostate. Okay, how do we get mathematical? Okay, again, all these simple things will be, you will see this again and again. So please pay attention. So for real thermal system, so real thermodynamic system, you have a much bigger number of coins, and you most likely have more than 2 outcomes. You don't have just head or tail. Okay, so if you, for example, if you take a piece of copper and ask yourself, a piece of copper, let's say 1 centimeter by 1 centimeter by 1 centimeter, you can ask how many atoms do you have in that volume, and that usually is easy to remember. because this number turns out to be a very convenient constant. So this is roughly Na particles or atoms in a typical lump, a typical piece of copper. Okay, take 1 centimeter by 1 centimeter. So the point is there are so many particles, 10 to the 23 particles there. And you should expect a very sharp peak, very, very sharp there. And if you want to specify a microstate, one microstate, you can imagine you need to give a long list, right? So for a small system, n equals 4, I already need 4 entries. That is only for the system with 2 outcomes. If I have such a big system, I will have a very long list. Okay, but the point remains. The point we want to appreciate is we have a large number, and we will still have the most probable macrostate. That macrostate will have the large number of microstates associated with that. Okay, so let's see how to do the mathematics for the two-level system. This is called the two-level system. This is a coin problem. So, and then we will do the second example, which is for a system with more than 2, possibly this. Okay, so if I do the coin problem and generalize to n coins, or we toss it n times. So coin problem again, coin problem. So we are going to toss the coin, the same coin n times. And this is a bit awkward for me to say. And we are going to get little n, which label the number of heads. Okay, how many microstates do we have associated with this general case? So for example, we can ask if we have 4, n equals 4, and I want 3 heads, how many number of microstates do we have associated with this macrostate? Okay, so the language is very precise here. Okay, so let me say this again. I can have n equals 4. I can have little n equals 3. Okay, big N equals 4. Okay, little n equals 3. And I can ask myself, how many microstates do I have? I want a formula to calculate this. And this is something you learn in high school, right? You know how to do this calculation, and you get this scenario here. You get 4. Okay, so I have n coins or n flips, and I want to get 3 heads. How many microstates do I have corresponding to these particular macrostates? Okay, so let me erase this, not to confuse you later. Okay, so we'll be careful of the language. So the number of microstates, I'm going to use this symbol microstates, is I have 4 coins. So how many combination how many different arrangement I can have to arrange 4 coins, distinguishable coins, or 4 symbols? So that will be n factorial. Okay, and I will have n heads, right? So how many, if I have n of them showing heads, how many different position I can place them? I have to divide them out to avoid overcounting. Okay, and I have 2 scenarios. So I have head I will also have tail, and the tail will have the same problem. I can have the tail, and the three tails will be the same. I have to divide them out to avoid overcounting. So I will have tail, number of tail factorial, but the number of tail factorial is the total number of flip minus the number of head factorial. Okay. You can try, put 4 factorial, right? 4 times, I want to get 3 head, 4 factorial, and then this 3 factorial, n minus 3 is 1, 1 factorial is 1, so 4 factorial divided by 3 factorial is 4. Okay, and this I'm going to call it omega k. This k is just an index for me to refer to a particular macro state. So this is this index labels a particular macro state, and this macro state I need to describe it for you, and the description is simply a macro state with 3 heads and 1 tail. Okay, now since this is a simple problem, I might as well use the number of head to label it. So I'm going to do that. I'm going to simply use omega sub 3 to say I have 3 heads, and it's understood that I will have 1 tail, or n minus 3 tails. Okay, so for coin. But this is a general notation we will use. Okay, and then the total number of microstates corresponding to all macrostates that will requires me to do the summation. Okay, so this is the big omega, this is a little omega, this is the big omega, and this requires me to sum over everything. Okay, this is just a label. It depends on how you want to label. Start from 1, start from 0, doesn't matter. This is just a label for the macrostates. So we need to consider all possible macrostates and then add them up. Okay, so for the coin, because I want to get a general formula, so I'm going to take large N case. So I'm going to look at large N for the coin too. Look at large N for the coin problem. And I'm going to treat this as a continuous function, really. I'm going to see this as a function of little n, and this n will be continuous. I don't want to care about the discreteness of this when I have a very large n. So I'm going to treat n, little n, as a continuous variable. Okay, what is my m here? My m here is to show you we can analytically get you the result you want. That is to say that the most probable macrostates will correspond to exactly half of the coin to have the head, the other half have the tail. This is based on your experience, but we can really do it analytically too, and this is really the heart of this calculation. Okay, how do we do that? I want to, now this is omega k, omega sub k, this is omega. Once I treat it as a continuous variable, I can write this as omega as a function of k, but k is n, so I would say this is continuous, this is a continuous curve, this omega. Okay, so what I want to do is I want to find the most probable macrostates. So I want to find the most number of microstates. That is to say, I have to maximize. I have to do calculus. I need to maximize maximize omega as a function of k, but k is n here. Okay? So once I maximize this, I will know the condition for having a maximum quantity. And hopefully you will recognize the result right away. Okay, so for this part is conventional to not to maximize omega, but equivalently or equivalently, we are going to maximize log of omega. The reason we can do that is because this is a monotonic function. Okay, so if omega is maximum, log of omega is also a maximum. So it's more convenient to maximize log of omega. Okay, let's just do that. Another thing is, as a preview, now log has an advantage because log, when we have log, we know we can use Stirling's approximation. Stirling's approximation, which says if you have log of x factorial, you have x log x minus x for large x. Okay, so we are really setting up the problem in a way that we can do all this. We want a large number, and then we will have factorial to worry about, and then we do the log rather than the function itself, in order to be able to use Stirling approximation. Okay, look, I want to maximize this thing, which means I want to maximize this expression, right? So I can see this as omega of n. Okay, so let's do that. Let's bring this up a bit and start the work. Okay, so let's do it. So I'm going to take this. I'm going to take this expression. I already have 2 star today, so 3 star. Okay, so the 3 star, I'm going to take the log of this. Log of omega will be log of n factorial minus log of little n factorial minus the log of big N minus n factorial. Okay, as I say, I treat this as omega as a function of n. So this omega is a function of n. I want to maximize it. Now here, let's do the Stirling. I'm not going to care about log of big N factorial because what I'm going to do next is to take derivative, and this n is a constant of the problem. I told you at the beginning I have n coins. I told you at the beginning that I flip the same coin n times. I told you at the beginning that we are doing microcanonical ensemble, which means the total number of particles is a constant. So this is the constant of the problem. Okay, I'm not gonna waste my life to do this. Okay, but this one I'm going to manipulate a little bit so I can take the derivative more easily. So I will have, this will be n log n, n log n minus n. There's a minus sign, so it's plus n. Okay, and then the second term I will have big N minus n, log of big N minus n, minus n, but there's a minus sign, so I add the plus, n minus n. Okay, so from this line, I didn't do much. This is just applying Stirling's approximation. Okay, so you see some nice cancellation already here. There's a n, little n, and a minus little n here. And again, this big N will disappear later. Okay, next I do the derivative of log with respect to little n. Okay, first term becomes 0. Second, I have to use the product rule. So first, I'm going to keep log n and differentiate n, I get 1. Then I keep n and differentiate log n, I get 1 over n. Okay, and then here I do the same. First, I keep log of m minus n, log of m minus n, big M minus n. Then I differentiate this, I get minus 1. So there's a minus sign here. And then I keep big N minus n. I differentiate this, I get n minus little n. And I have to differentiate this again, I pull out a minus sign. Okay, and then this big N is gone. So let me put this in for you. Okay, so here you have this is minus 1. This is minus 1, and this one is minus 1 and minus sign here. So this whole thing is plus 1. So they cancel. Okay, so this one cancel this whole thing here. Okay, so the end result is there. You have this term is log n. This one is plus log of big N minus little n. Okay, and this is a log of n minus n divided by n. And you do optimization, so you need to set this to 0. Okay, so this is a condition. Okay, so you have n minus n divided by n. This has to be 1. Okay, so you move this n here and move this n to the other side. You have 2 little n. 2 times little n is big N, so n is big N divided by 2. So this is what we want. Okay, so the most probable state is as what we expected. You will have the half of the flips will give you head, the other half will give you tail, as what we expected. Okay, and this is this page. You will do it many times later on. So the same trick is also how we what you are looking at the screen now. Of course, with suitable modification, will actually lead to three important equilibrium distribution functions, namely Maxwell-Boltzmann, Fermi-Dirac, and Bose-Einstein. You are going to use this trick again and again and again to get that. Okay, but there requires us to also talk about constraints and what are the constraints you put in. And there you will not have this 0 here. You will have something set by the constraint. That's why you will have some exponential coming in. This is already probably, hopefully reminds you that for Boltzmann factor, you have an exponential term. And that is precisely because of all these log term coming in. Okay, so this is, I think this is a really fun part. Huh? Let me put this here. Okay, but this is still very simple. Simple, but we are going to use it, really. We are going to use it soon. But let me say something a little bit more complicated still about distinguishable particle. But now we want more than the coin. So more complicated than the coin. Complicated than the coin problem. Okay, how complicated can you have? So for example, I can consider, this is the next one I want to consider. I want to consider a system such that I have J energy levels. Okay? And for the entire system, I have N particles. And each of them can be occupying these J energy levels. Okay, that is to say I have more particles, and now I have more arrangement that I can do. I can make my system more realistic, more and more realistic, and more interesting. So let me give you a picture. For example, I can talk about something like this. So like this. Okay, I can talk about first a simple one, and then I'm going to do a general case like the coin problem. So for example, I can consider something like this. I can have only 3 particles. Okay, and how do I make sure these particles are distinguishable? I need to find a trick. So the model here is actually like this. This kind of model will be applied to the case of, say you have a lattice, and then on the lattice you have your atoms. So you have some atoms localized on a lattice. Okay, so let me draw you a simple lattice. So for example, this is a lattice, a cubic lattice. Okay, so and this goes on forever. This is just 1 unit. I can one case of having this picture, to apply this picture, is to look at this atom here and this atom here and this atom here. And if I just pick 3 of them, each of them can be on a potential well described by this. Okay, so if I label this 0 for us. Suppose, imagine you have you don't set this to 0. This is I choose this for convenience. If you start from epsilon and you go up like this, and this is, suppose this is the lowest energy level, you basically have a harmonic oscillator. This is the potential well of a harmonic oscillator. If unfortunately I choose this example of having a 0. Suppose the lowest one is finite, you have your 0 point energy, and this is the problem of harmonic oscillator. Okay, and this is a realistic picture, because when you put your atoms on the lattice, you can form crystal. Okay, and this formation of crystal really means you are the atoms are seeing some kind of potential. Okay, and this potential is due to the interaction with the neighbor, and this interaction is because of the chemical bond. And this chemical bond is usually modeled using springs. And if you have springs, you have this kind of harmonic oscillator potential. Okay, so if we don't worry about the detail of that, you will just simply do statistical mechanics with this kind of energy levels for n particles. Okay, so this will go up, and if you go up, you have J times epsilon. Okay, so still, I don't want to go too general, but this is just to motivate you uh, uh, in order to think about this as a potential for real application. So if I want to step back and look at something I can manage easily by listing everything out, I will look at the case of 3 particles. So n equals 3. 3 particles. Okay, so they are distinguishable, so I can say I can label them because they are distinguishable. I know the address. So this is site A, site B, site C, and this is particle A, particle B, particle C. And the energy level spectrum is given by this. That is to say, I can label them by this number J. So I will say the energy spectrum is given by E sub J, such that E sub J is J times epsilon. Okay, again, simple case. You can say artificially created for me to get the mathematics done easily. Okay, and this is a time when I can introduce constraint. What are my constraints? Okay, constraint is something I artificially put into. Again, I will choose something I can manage. But first, the general constraint is this. In the spirit of this constant n, constant v, constant u, the micro canonical ensemble, the constraints are the following. U, total internal energy. In the non-interacting case, is simply the number of particles occupying the energy level epsilon, and this product will give me the interaction, will give me the total energy in the non-interacting case. Okay, so that is to say I will send someone to walk around this lattice and I will ask how many particles in total are in the ground state. So I will ask, okay, then ground state here turns out to be 0, so I don't count. How many of them will be in the energy level epsilon? So if there are 2, then I will have 2 times epsilon contribution. And then I keep asking this question. Okay, but I say this is a constraint. So this constraint means I have to set this to be a constant. Okay, another constraint is this. The total number of particles has to be a constant too. So I will have simply this. Again, I ask how many of them occupying energy level J, and at the same time, I write down this number for me to do the accounting. And this has to be a constant too. Okay. Now this is the general case. We are going to do this mathematics in a general way. That is to say, when we do the constant, when I do the differential du, I will have d constant, so du is 0, dn is 0. These are the 2 constraints, and I still have to maximize the total number of microstates, just like what I did before. So I have another differential d log something, right, like before for the coin problem. Right? D log omega has to be a constant. It has to be 0. Okay, so I will have, I need to optimize that subject to 2 constraints. And this is the mathematics of Lagrange multiplier. So we are going to do these multipliers eventually. Okay, and this is, and then we'll get the equilibrium. We will get the equilibrium distribution subject to this constraint. And before we do that, I would like to gain some insight by doing something more artificial but easier to handle. So for example, I can say, let's investigate the system, which is small enough. So small enough, 3 potential well. 3 particles. I'm going to set it to 3 so you can write everything down. I hope you will. And to make your life easier, I'm going to set this total amount of internal energy. I'm going to set it to 3. I can set it to other numbers. This is just for you to guess what you get by writing everything down. Just like you wrote down the case of the coin, you know, the most probable situation, the most probable macro state correspond to the one with half the number of head and half a number of tail. And if you do the same, you will be able to guess some kind of distribution. Okay, so this is something we won't have time to do much, but I encourage you to think before looking at the note. The note has some detail already, but if you go through this yourself, it will be really good. Okay, so before I end, I will just, for example, how do you write this down? You need to write down all the possible microstates. What are the possible microstates? Okay, so this A, B, C. One possibility is I have my particle A here. Okay, and this is 3 epsilon. I will have no other energy for the other 2. So the other 2 has to be occupying this. Okay, so this is one microstate. And how do you express this mathematically? I will let you think about this. Okay, I can also have another microstate. This is one possibility because I respect this constraint. Okay, and you can see there are other ways to do things. For example, A is this, B is this, C is this. Okay, this is another microstate. Okay, and keep doing this, and hopefully you get some feeling about what is the most probable macrostate. That is to say, how do you get that situation with the maximum number of different arrangement, different configurations, or different microstates. Okay, so on Monday, we will pick up from here. All right? Okay, that's all for today. Thank you very much.